This is third and last module of chapter 4. In this module, we shall consider a system of nonlinear equations, particularly a pair of nonlinear equations. The solution of or to finding a root of a nonlinear equation, particularly system of nonlinear equation, is a very difficult task, because for a pair of nonlinear equation, the equation may represent two surfaces in 3 dimensions, and these two surfaces may intersect at one or more points. So, to find such points in 3 dimensions is nothing but a very difficult task. Now, we shall describe 3 methods. The first method is called the iteration method, second one is Seidel method, and third one is Newton-Raphson method to find a root of a system of nonlinear equation, particularly a pair of nonlinear equation. I have mentioned that finding a root of a nonlinear equation is a very difficult task, and it becomes more difficult if the system of equation is nonlinear equations. The nonlinear equation f(x) equal to 0, that means nonlinear equation containing one variable, represents a plane curve, and if the equation cuts the x axis at the point x1, 0, then x1 is the root of the equation. So, it is obvious, and many methods are developed to find this type of problem or to solve this type of problems. But a pair of nonlinear equation f of x comma y equal to 0 and g of x comma y equal to 0 represent surfaces in 3 dimensions. A point of intersection of these surfaces is the solution of the equation, that means the root of the equations. But it is a very difficult task to find such point of intersection in case of pair of or higher order or higher number of equations. Now, we consider fixed point iteration method to find a root of a pair of nonlinear equations. The nonlinear equations be f of x comma y equal to 0 and g of x comma y equal to 0. The function f of xy and g of xy are either algebraic or transcendental. Like fixed point iteration method, these equations are written as x equal to phi of xy and y equal to psi of x comma y. But the function phi and psi are not unique. The equation f of x comma y equal to 0 and g of x comma y equal to 0 can be written in many different ways to get phi and psi. All such representations are not acceptable, but few of the representation can be taken as the iteration scheme. For example, let f of x comma y equal to x square y plus 2x plus 3 equal to 0 and gx equal to xy plus e to the power x minus y square equal to 0. The first equation can be written as x equal to half into y minus x square y, and this equation can also be written as x equal to square root of 3y minus 2x by y. And similarly, the second equation can be written as y equal to square root of xy plus e to the power x, or it can also be written as y equal to 1 by x into y square minus e to the power x. And many other representation can also be obtained for these two functions. Here only 2 alternatives are given. Now, let xi eta be an exact root of the pair of equations mentioned in equation number 1, and let x0 y0 be the initial guess for this root. Then the first approximate root x1 y1 is then determined as x1 equal to phi of x0 y0 and y1 equal to psi of x0 comma y0. So, these are the first approximated root obtained from the function phi and psi. Similarly, the second approximate root is given by x2 equal to phi of x1 y1 and y2 equal to psi of x1 comma y1, and so on. In general, xn plus 1 equal to phi of xn comma yn and yn plus 1 equal to psi of xn comma yn. So, this is the general expression to get the values of x and y at the n plus 1 iteration. Thus, the fixed point iteration method generates a double sequence of numbers which is represented as xn comma yn, and if the sequence, that means this double sequence, is convergent to a number then that number is the exact root of the equation, and this equation should satisfied by the exact root xi and eta. That means xi equal to phi of xi comma eta and eta equal to psi of xi comma eta. The rate of convergence of this method can be determined, but one interesting thing or one important issues of this method is there is no guarantee that the sequence xn yn will converge to a root. The sufficient condition for convergent is stated below. Let R be a region which contains the exact root xi eta. Assume that the function x equal to phi x comma y and y equal to psi x comma y and their first order partial derivatives are continuous within the region R, and if the initial guess x0 y0 is sufficiently close to the exact root xi eta and the absolute value of partial derivative of phi with respect to x plus absolute value of the first derivative of phi with respect to y is less than 1 and first partial derivative of psi with respect to x and its absolute value plus the absolute value of the first partial derivative of psi with respect to y is less than 1 for all values of x, y within the region R, then the iteration scheme xn yn obtained from the equation 1 converges to the exact root xi eta. In case of 3 equations or 3 variables, the sufficient condition for convergence of the function x equal to phi of x comma y z, y equal to psi of x comma y z and z equal to zeta x comma y z is absolute value of first derivative of phi with respect to x plus absolute value of first derivative of phi with respect to y plus absolute value of phi with respect to z less than 1. Similarly, the condition is true for the other function psi and zeta, and this condition must satisfied for all values of x, y, z within the region R. Now, I consider one example to illustrate the fixed point iteration method to find a root of the equation, a pair of equations. The first equation is x square plus y square minus 4x equal to 0, and second equation is x square plus y square minus 8x plus 15 equal to 0. And we assume that the initial guess for x equal to 3.5, that means x0 equal to 3.5 and y0 equal to 1.0. The first equation can be written as x equal to 2 plus square root of 4 minus y square, and second equation can be written as y equal to square root of 1 minus x minus 4 power 2. So, for this case the function phi of x comma y equal to 2 plus root over 4 minus y square and psi of x comma y equal to root over 1 minus x minus 4 whole square. So, these are the functions which are to be used in the iteration scheme. The iteration scheme is xn plus 1 equal to phi of xn comma yn equal to 2 plus root over 4 minus yn power 2, and the iteration scheme for y is yn plus 1 equal to psi of xn comma yn equal to square root of 1 minus xn minus 4 power 2. So, these are the iteration formula to find the values of x and y. All the values of xn, yn, xn plus 1 and yn plus 1 for all n equal to 0, 1 up to 11 are calculated in the following table. The first row represents the values of x0, y0, x1 and y1, and last row represents the value of x11, y11, x12 and y12. So, from the last two rows we see that the iteration scheme converges to the root 3.75000, 0.96825. So, this is a root correct up to 5 decimal places. Now, the above method can be accelerated by modified the iteration scheme 1 by minor modification of this previous iteration scheme. We can consider the new iteration scheme. When yn plus 1 is computed, then the value of xn plus 1 is already available. So, we can use this updated value of x to calculate the value of yn plus 1. Thus, the modified iteration scheme is xn plus 1 equal to phi of xn comma yn and yn plus 1 equal to psi of xn plus 1 comma yn. Note that in equation 3, the first argument of psi is replaced by xn plus 1 instead of xn, which is used in fixed point iteration method. This is the modification in Seidel iteration, and this iteration is called the Seidel iteration. And in case of 3 variables, the iteration scheme is extended as xn plus 1 equal to phi of xn comma yn comma zn. The iteration scheme for y is yn plus 1 equal to psi of xn plus 1 comma yn comma zn, and for the last variable z, the iteration scheme is zn plus 1 equal to g term xn plus 1 comma yn plus 1 comma zn. Here we consider the same example which is considered in iteration method. The equations are same as well as the starting point is same, and we shall solve this system of equation by Seidel iteration method. The first equation can be written as x equal to 2 plus root over 4 minus y square, and the second equation is y equal to root over 1 minus x minus 4 whole square. Therefore, phi xy equal to 2 plus root over 4 minus y square, and psi xy is equal to root over 1 minus x minus 4 power 2. Thus, the iteration scheme is xn plus 1 equal to phi of xn comma yn, which is equal to 2 plus root over 4 minus yn square, which is exactly same as the iteration method, but the second iteration scheme is changed. That means yn plus 1 equal to psi of xn plus 1 comma yn, which is equal to root over 1 minus xn plus 1 minus 4 power 2. So, here xn is replaced by xn plus 1 in Seidel iteration scheme. The value of xn, yn, xn plus 1 and yn for different values of n are shown in the following table. The first column represents the iteration number, second column represents the value of xn, and the next column are the values of yn, xn plus 1 and yn plus 1. Note that this iteration scheme converges at iteration number 6, and the convergent values of xn plus 1 and yn plus 1 are 3.75, 0001, and the value of yn plus 1 is 0.968246. Therefore, a root correct up to 5 decimal places obtained by Seidel iteration scheme is 3.75000, comma 0.96825. So, this is the root correct up to 5 decimal places, and the number of iteration used in Seidel method is 6, and the number of iteration used in iteration method, fixed point iteration method is 11. So, for the same example, we have seen that the Seidel iteration method gives more rapid convergence scheme than the fixed point iteration scheme. Two iterative methods, first one is called fixed point iteration and second one is called Seidel iteration methods, are described to find a root of a system of nonlinear equation, particularly a pair of nonlinear equations. But the main drawback of this method is to find the function phi and psi starting from the equation f of x comma y equal to 0 and g of x comma y equal to 0. Now, it describes another method called Newton-Raphson method. This method is free from finding such phi and psi, but the Newton-Raphson method takes the partial derivative of the function f and g. Now, we describe Newton-Raphson method to find a root of a pair of nonlinear equations. Let f of x comma y equal to 0 and g of x comma y equal to 0 be a pair of nonlinear equations. Also, let x0 comma y0 be an initial guess to the exact root xi term, and if h0 and k0 be the errors at x0 and y0 respectively, then x0 plus h0 and y0 plus k0 is a root of the given equation. Since x0 and y0 are approximate root or initial guess, and if h0 and k0 are the correction, and if the corrections are exactly evaluated from any method, then x0 plus h0 is the exact value of x and y0 plus k0 is also the exact value of y. But if these two values are not exact or approximate, then x0 plus h0 is an approximate value of x, and similarly second one is the approximate value of y. Now, from the equation 5, we have f of x0 plus h0 comma y0 plus k0 equal to 0, and g of x0 plus h0 comma y0 plus k0 equal to 0. Assume that the functions fxy and g of xy are differentiable. Then by Taylor series expansion, f of x0 comma y0 plus h0 into del f del x evaluated at the point x0 y0 plus k0 into del f del y evaluated at x0 y0 plus dot 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 equal to 0. And similarly from the equation, second equation of previous slide, the expansion of the function g is g of x0 comma y0 plus h0 into del g del x at x0 comma y0 plus k0 into del 0 del y evaluated at x0 y0 plus dot 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 equal to 0. Here also the values of h0 and k0 are small. So neglecting square and higher order terms of h0 and k0, the above equations reduce to h0 into del f0 del x plus k0 into del f0 del y equal to minus f0, where f0 is equal to f at the point x0 comma y0. Similarly from second equation of 7, we obtain h0 into del g0 del x plus k0 into del g0 del y equal to minus g0, where g0 equal to g at x0 comma y0. Note that all the partial derivatives are evaluated at the point x0 comma y0. So this is the system of linear equation, and these equations can be written as a matrix notation shown below. The first one is a 2 by 2 square matrix whose first row is del f0 del x, del f0 del y, second row is del j0 del x, del g0 del y into the column matrix h0 k0 equal to the column matrix minus f0 g0. So this is a system of equation in matrix form. So solving this equation, we can find the value of h0 and k0, or we can use any other method to find the value of h0 and k0. So using Cramer's rule, the values of h0 and k0 are obtained as follows: h0 equal to 1 by j0 into a determinant of order 2 by 2 whose first column is minus f0 minus g0, second column is del f0 del y and del g0 del y. Similarly, k0 is this expression and j0 is the determinant of the coefficient matrix of order 2 by 2. Therefore, the first approximative value of x is x0 plus h0, and the value of y is y1 equal to y0 plus k0. Since the values of x0, h0 and k0 are approximated values, and this is obtained by neglecting the higher powers of h0 and k0, therefore, we obtain the first approximated value, and that value is denoted by x1 y1, where x1 equal to x0 plus h0 and y1 equal to y0 plus k0. So this is the first approximated value obtained by Newton-Raphson method, where h0 and k0 are evaluated in first slide, previous slide. Similarly, the second approximate root is given by x2 equal to x1 plus h1, y2 equal to y1 plus k1, where h1 is given by this expression, k1 is given by this expression, and j1 is the determinant of the coefficient matrix, where f1 is evaluated at the point x1 y1, that means f1 equal to f of x1 comma y1 and g1 equal to g of x1 comma y1. In general, the n plus 1th approximate root xn plus 1 comma yn plus 1 is given by xn plus 1 equal to xn plus hn and yn plus 1 equal to yn plus kn, where hn equal to 1 by jn into a determinant of order 2 by 2 whose first column is minus fn and minus jn, second column is del fn del y, second element is del gn del y. Similarly, kn is given by this expression, and jn is the determinant of the coefficient matrix evaluated at the xn, yn point. This method, that means the Newton-Raphson method, will terminate when absolute value of xn plus 1 minus xn is strictly less than epsilon, and absolute value of yn plus 1 minus yn is also strictly less than epsilon, where epsilon is a very small positive pre-assigned number called the error tolerance. So, depending on the values of epsilon, we can terminate the iteration process. Now, we state the sufficient condition for convergence of Newton-Raphson method. Suppose R be a region which contains the exact root xi eta, and let x0 y0 be the initial guess to the exact root xi eta of the equation f of xy equal to 0 and g of xy equal to 0. If the first condition is the function f, g and their first order partial derivatives are continuous and bounded within the region R, and also then the determinant of the coefficient matrix at the point xn yn is not equal to 0 within the region R, then the sequence of approximation xn plus 1 equal to xn plus hn, comma yn plus 1 equal to yn plus kn converges to the root exact root xi eta. So, this is the sufficient condition for the iteration scheme to converge to a root. Now, we consider one example to illustrate the Newton-Raphson method to solve a pair of nonlinear equation. The equations are 3x square minus 2y square minus 1 equal to 0. Second equation is x square minus 2x plus 2y minus 8 equal to 0, and the initial guess is taken as x0 equal to 2.5, y0 equal to 3.0. Here fx equal to 3x square minus 2y square minus 1 and gxy equal to x square minus 2x plus 2y minus 8. Therefore, del f del x equal to 6x, it is obvious. Del f del y equal to 4y obtained from the first expression or first function. Del g del x equal to 2x minus 2 and del g del y equal to 2. Therefore, the coefficient matrix is a 2 by 2 matrix whose first row is 6x minus 4y and second row is 2x minus 2 and 2. Now, at the first iteration, we evaluated all the values, that means the values of the coefficient matrix, the values of f and g at the point x0, y0, and in this case minus f0 and minus g0 are 0.25 and 0.75. Therefore, the system of equations is given by the first matrix is a 2 by 2 matrix, coefficient matrix, whose first row is 15 minus 12, second row is 3 2, and the unknown column matrix is h0 k0, and right hand vector is minus 0.25 and 0.75. Since J0 equal to 66, the value of determinant of the coefficient matrix, therefore, by matrix inverse method we can obtain the values of H0 and K0 as this one. After simplification of this product of the matrices, we obtain 0.143939 and second element is 0.159091. Therefore, the first approximate value of x1 equal to x0 plus h0, which is equal to 2.5 plus 0.143939, which is equal to 2.643939, and the first approximate value of y1 is y0 plus k0 equal to 3 plus 0.159091, which is equal to 3.159091. So, we obtain the first approximate value of x1 and y1. Now, at second iteration, that means at the point x1, y1, the value of minus f1 equal to minus 0.011536 and the value of minus g1 is equal to minus 0.020719, and the matrix equation is this one, which contains a 2 by 2 matrix, coefficient matrix is of order 2 by 2, and the column vector, unknown vector is h1 k1 and right hand vector is known, whose values is mentioned in first line. Solving this system of equation, we get h1 equal to minus 0.003888 and the value of k1 is equal to minus 0.003968. Thus, the second approximate value of x, which is x2, and it is equal to 2.640052, and the second approximate value of y, which is equal to 3.155123. In third iteration, we get the value of h2 equal to minus 0.000003 and k equal to minus 0.000003. Note that h and k, particularly h2 and k2, represents the error occur in the successive iteration. So, note that the amount of error or magnitude of the error in h or in k are very small and correct up to 5 decimal places. Therefore, the third approximated value of x, which is x3, is equal to 2.640049, and the value of y3, which is equal to 3.155120. So, one root of the given system of equation is x equal to 2.64005 and y equal to 3.155120, correct up to 5 decimal places. So, this is the root obtained by Newton-Raphson method and needs only 3 iterations. In this module, we have described 2 iteration methods to solve a pair of nonlinear equations. The first method is called the iteration method, and after modification of iteration method, we get the another iteration method called Seidel iteration method. The rate of convergence of these iteration methods is 1. But the main drawback of this method is to find the function phi and psi, and which are not required in the Newton-Raphson method. But the Newton-Raphson method involves to calculate the first order partial derivative of the functions, and this derivative is not required in the first two method, iteration method and Seidel method. And many other methods are available to solve a system of nonlinear equations in literature. For further references, the reader can consult the learn more section of the module.